So in continuation from Carnot cycle, this is a Rankine cycle. Okay. Here, some of the impracticalities associated with the Carnot cycle can be eliminated by condensing the steam and completely in a condenser. Okay, and then compressing the liquid to the boiler pressure. Okay, compressing the liquid from here to the boiler pressure, and in a small feed pump. And with this, the isentropic nature from point 1 to point 4 changes. Okay, so meaning that we are able to compress the liquid completely at this point. So between these 3 to 4, we make sure that all the total amount of heat that needed to go to get this liquid vapor mixture to a liquid state. Okay, and that means when it gets to the pump, is now a liquid which can then be pumped, okay, or compressed to the boiler pressure to the stage. So this is an idealized cycle for vapor power plants. It is called the Rankine cycle. So the usual thing that happens within the cycle here, okay, but the change is now is from the boiler, we get the saturated vapor which goes in the turbine, does a work, and from point 3, which is the condensation stage, and all the liquid vapor mixture is condensed to liquid, and that is fed to a pump and is brought to a pressure uh, of the boiler pressure, and that is heated up to the boiler pressure as well. Okay, so the total heat in goes at stage 1 here, between 1 and 2, and between 2 and 3 the work done by the fluid as usual leaves, and between 3 to 4 the condensation, the heat loss, the removal of heat. Then the pump work goes in between 4 to 5. Okay, so the heating of the fluid in the boiler is now represented from 5 to 2, from this point to this point. And then the ideal Rankine cycle does not involve any internal irreversibilities. Okay, there are no internal irreversibilities. So this means that the saturated liquid vapor mixture at stage 3, okay, enters the condenser. The fluid is then cooled reversibly isothermally, okay, reversibly isothermally at constant temperature in the condenser at constant pressure. The condensation process is now completed. So the fluid leaves the condenser as a saturated liquid as it enters stage 4. So the saturated liquid at stage 4 enters a small feed pump at this stage, and the pump, it is compressed isentropically. So the pump from point 4 to point 5 has similar value for entropy. Okay, so the fluid temperature and the pressure increases somewhat during this isentropic compression, and the fluid leaves the pump as a compressed liquid. Now the compressed liquid is at stage 5, enters the boiler. So in the boiler, it is heated at constant pressure isothermally, and constant pressure and non-isothermally. As you can see, the temperature rises from this state to that state. Okay, then isothermally to stage 1 and remains isothermal. So non-isothermal from stage 5 to 1 and remains isothermally till 2. Okay, so example of Rankine cycle uh, which operates between 30 bar and 0.04 bar. Calculate the heat transferred in and out of the system per unit mass, the work transfer in and out of the system per unit mass, the cycle efficiency, the specific steam consumption, and the work ratio. So the Rankine cycle operates between 30 bar and 0.04 bar. Now we know the high temperature region and the low temperature region. Okay, so how can we calculate the heat /work transfer for each process in the cycle? So we know that at the heat inlet from 5 to 2, then the change in enthalpy from zero point 0.5 to 2 will give us the total heat added to the system. And the work out of the system is the difference in enthalpy at stage 2 and 3, and the heat loss as a result of the condenser removing heat from the uh, working fluid, then is the change in enthalpy at stage 3 and 4, which is given as this. Now the work done to the system to get it to the boiler pressure is done here between stage 4 and 5. Okay, so we apply the first law as usual, and as you know, the potential and kinetic energy, we assume them to be zero due to no difference in height in the equipment and no significant increase in velocity within the system. So for the stage 1, we calculate based off of the pressure, which is 30 bar. We go to the steam table as usual, and we find 30 bar pressure. This pressure, we find 30 bar pressure, and we read off the enthalpy of the fluid, the enthalpy of the gas phase, the entropy of the liquid, and the entropy of the gas. But in this case, because it's a compressed liquid, we only focus on the enthalpy of the liquid and the entropy of the liquid. Okay, so enthalpy of the liquid and the entropy of the liquid. So at stage 2, we do similar thing. We find the stage 2 is saturated vapor only. So we read out the value of enthalpy and entropy when the pressure is 30 bar from the steam table. So at stage 3, we know that there is a pressure decrease in pressure at zero. So the new pressure is 0.04 bar, and at this point, we know that we have a mixture of saturated liquid and vapor, so which enters the condenser. What we do here is we convert this. We look on the steam table. Okay, at 0.04 bar, we go up here. Pressure bar 0.04 bar. So we read out the value of enthalpy. Okay, enthalpy of the liquid, enthalpy of the gas phase, entropy of the liquid, and entropy of the gas phase. And once we do, we list them all out here. But because the saturated vapor that left here lost quality, we need to identify the dryness fraction of that steam. Okay, and we can use this equation to do so. Plugging in the values that we found from the steam table, we arrive at this 71.6%, and we can use that to calculate the enthalpy of this steam here at stage 3. So once we calculated this, then we can move on to calculate the enthalpy at stage 4. So we know that there's the mixture of liquid vapor here has been fully condensed. So what we have here is at stage 4 is saturated liquid. So we go back to the steam table again to find the corresponding values for the enthalpy and the entropy at this particular pressure, which is 0.04 bar. So at stage 5, there is a pump work done. So we need to calculate the pump work. Since we know the enthalpy at stage 4, what we need to calculate the work done by the pump to get the liquid compressed up to the boiler pressure, operating pressure of the boiler. And we need to use this formula, change in pressure multiplied by the constant volume, specific volume in this case. Okay, and if we convert the pressure from bar to pascals for these 2 points, and we can take the difference in that and we give us the change in pressure. Now we know that this is water, and we can assume that the inverse density of water at this constant temperature obviously will be with 1000. Okay, and if we use that value, we can calculate for the power, the work done by the pump to get this saturated liquid to a compressed liquid. Okay, so and that will give us a minus 3 kilojoules per kilogram. So since we have all our enthalpies calculated, and we can now calculate the heat transfer in and out of the system. So the total heat supplied to the system, we can calculate that by taking the difference in enthalpies between the stages 5, 1, and 2, and that gives us a change in enthalpy between uh, stage 2 and stage 5, and that gives us the value of 2679 kilojoules per kilogram. We do the same for the total heat removed by the condenser, and that is between stages 3 and 4, and we take the change in enthalpy, which is H4 minus H3, and it gives us this value. So for the work transferred in and out of the system, so the useful work done by the steam in the turbine at stage 2 here, we need to calculate that. That gives us the change in enthalpy between stage 2 and 3, and it gives us a value of 940 kilojoules per kilogram. And the work done by the pump to compress the saturated liquid to compressed liquid, which we've already calculated previously, and gives us a minus 3 kilojoule per kilogram. So calculating the cycle efficiency, we know the net work done by the network in the system, and we divide that by the total heat added to the system, and it gives us a 35% cycle efficiency. The rate of steam consumption, we use the formula and taking into account the absolute value that should be in the bottom, so any negative sign cancels out, and we arrive at close to 4 kilogram per kilowatt hour. So the work ratio, which is given as the net work divided by the work out of the system, and we plug in the values and we get 0.997. So the work ratio concludes the example 2. So in the Rankine cycle, not all the heat supplied is transferred at the upper temperature. As a consequence, the efficiency of this cycle will be less than that of a Carnot vapor cycle operating between the same temperatures. Some heat is added while the temperature of the liquid varies from temperature at 5 to temperature at 1. Okay. So with the compressor replaced by a smaller feed pump at this stage, the pump work time is very small compared with other energy transfer in the cycle. So when the boiler pressure is comparatively low, a good approximation to the ideal cycle efficiency will be obtained if the pump work is neglected. So comparing the areas of the two cycles, it is clear that the net work output per unit mass of steam is greater in the Rankine cycle, because the area in the middle, as you can see here, shown in this diagram. So the result in a lower steam consumption and a higher work rate ratio. Although the ideal cycle efficiency is lower, the actual cycle efficiency may not be so different, and the size of the Rankine plant will certainly be much smaller. Okay. So the following impracticalities remain with this cycle. The turbine has to handle steam with a high moisture content, that is the liquid droplets impinging in the turbine, okay, turbine blade causing erosion and is a major source of wear. Limiting the heat transfer process to two-phase system limits the maximum temperature that can be used in the cycle, okay. So this limits the thermal efficiency because of the difference between the Carnot cycle. As you know, at this stage you have a low quality steam, but in Rankine cycle the compression is total compression, so you have saturated liquid at this point. Okay, so many of the impracticalities associated with the Carnot vapor cycle and the ideal Rankine cycle can be eliminated by condensing the steam completely in the condenser, compressing the liquid to the boiler pressure in a small feed pump at this stage, and superheating the steam in the boiler. Okay, uh, this is the ideal cycle for vapor power plant. So it is called the Rankine cycle with superheat. So the Rankine cycle with superheat is presented here in the scheme here. So we have the boiler, and here we can add additional heat between stages 4 and 5 to superheat the steam that is leaving the boiler. So the high quality steam now goes into the turbine to do the work. At the Cs, the low quality steam comes out with the compression, with the condensation here, taking it back to the pump, and the pump taking it back to the boiler at the operating condition. So the boiler together with the superheater is often called the steam generator. And as you can see on this temperature entropy diagram, the inclusion of this superheat, the heater, additional heater to superheat the steam is included in the diagram as well, okay? Because at this stage, when it goes, before it goes into the turbine at stage 5, then there is a change in temperature as a result of that additional heating done to the steam leaving the boiler, okay? So heating of the fluid in the boiler is now represented through stages 2 to 5. Okay, so the 2, 3, the boiler, superheating, and here the turbine. Then the ideal Rankine cycle with superheat does not involve any internal irreversibilities. Okay, so stages 2 to 5, as we've highlighted, the compressed liquid at stage 2, okay, coming from the pump here, uh, in the it enters the boiler. Okay, in the boiler it is heated at a constant pressure, non-isothermal, so there is a change in temperature from the boiler here up to this stage now until it gets to saturated liquid at stage 3. So isothermally, it is boiled, or temperature is the heat is added isothermally, that is a constant temperature, as you can see here, until it becomes saturated vapor at stage 4. Now, a non-isothermal heat addition to superheat that steam to get the best quality steam out of this, uh, get a superheated vapor, uh, gets it to the turbine at stage 5. So the stages 5 to 6 is an isentropic process, okay, and this is where the superheated vapor at stage 5 enters the turbine. Then in the turbine it expands, okay, to do useful work, and the pressure and the steam and the temperature of the steam drops drastically, as you can see. It goes down to this at this temperature here. But it does that at a constant, or at a constant entropy. Okay, so the fluid typically leaves the turbine as a saturated liquid vapor mixture. So and that saturated liquid vapor mixture enters stage 6, which is the condenser. So example 3, an ideal Rankine cycle with a superheat operates between 30 bar and 0.04 bar. The steam is superheated to 450 degrees Celsius before entering the turbine. So calculate the heat transfer in and out of the system per unit mass, the work transfer in and out of the system per unit mass, and the cycle efficiency, and the specific steam consumption, the SSC, and the work ratio. I know by now we would have understood all the areas that within under the Rankine cycle here with superheat that categorizes the heat addition, heat removal, the work done by the turbine, and the work done by the steam in the turbine, and the work done by the pump at this stage. Okay, so if we do similar thing we've been doing before, then we can draw the scheme, draw the cycle on a TS diagram, indicating all the major areas. Then what do? We use the first law of thermodynamics to analyze the process. And here we make the assumption that kinetic energy, no change in velocities throughout the flow, or minimal changes in velocity, which accounts for very tiny change in kinetic energy. Then potential energy, no difference in heights of flowing pipes, so we neglect that as well. So meaning that the enthalpy is the key thing that we need to use to measure either the heat added to the system or the work done by the work done. Okay, so we first of all, what is the total work done to the working fluid? And that is the pump work, and that is between stages 1 and 2, and it's giving us the change in enthalpy between 1 and 2, so which is given here. So what is total heat added? So that is from stage 2 to 5, and that is given as the change in enthalpy between stage 2 to 5, and is represented here. Now the work done by the working fluid, the steam in this case in the turbine, is giving us a change in enthalpy between 5 and 6. Then the condensation, the removal of heat from the fluid to condense it to liquid, saturated liquid, is given as the enthalpy, the change in enthalpy between stages 6 and 1, as given here. Okay, so going back to the steam table as usual, by now we should know how to find these values at steam table. So since we know the initial pressure at the entrance, okay, which is 0.04 bar at stage 1, then we find it, and we know that there is a total condensation of the liquid vapor mixture to saturated liquid. Then we go to steam table and find the corresponding values for the enthalpy and entropy when pressure is 0.04 bar for a saturated liquid, and that is given as this. Now we go further to stage 2. So what do we have at stage 2? So the pump work increases the pressure from 0.04 to 30 bar, which is the operating pressure of the boiler. And based on that, we know that once the saturated liquid is compressed by the pump, then we'll be left with compressed liquid. So we go to steam table for 30 bar. We find the corresponding enthalpy at point at this stage 2. And to calculate that, we need to add the work done by the pump plus the original enthalpy at stage 1. So we know the enthalpy at stage 1 at 0.04, then there is a work done by the pump, and the work done by the pump is giving us the change in pressure times the specific volume of the saturated liquid at stage 1. Okay, so if we do that, we know that the pressure changed from 0.04 to 30 bar, and we can do with this formula we can calculate that work, so which is the minus change in pressure at point 1 and 2 times the volume, the specific volume at stage 1 and 2. Okay, it's going to be the same specific volume, so because it's a saturated liquid, so there is no mixture, so it's going to be the same amount of specific volume here. So but what do? We calculate, we plug in the values for the known pressure, then for the specific volume of saturated liquid here, we can guess, okay, because the temperature here, corresponding temperature of the average temperature, if you want to be specific, okay, you can do a kind of average pressure between these, which will give you 30 bar and 0.04 bar. Then you find that corresponding temperature, okay, for the average pressure you've calculated, and that will be the saturation pressure. Then you find the corresponding temperature. Based on that, you can go to steam table and read out the density of liquid water at that temperature. Okay, that's if you want to be specific. And whatever density it gives you, if you take the inverse of that density, that will give you the specific volume. Okay, but in this case, you can make a clear assumption to say that the density of water is 1000. And if you check steam table, okay, if you check steam table, you will find out that let's go to further properties of water. Let's blow this up. You find out that we have the specific volumes here. You see that if you check for, if you take let's see 30 bar falls between this, you need to interpolate. But whatever figure you get, which will not be far away from the average pressure of 30 bar plus 0.04 bar divided by 2. So it wouldn't be far away. The average wouldn't be far away from 30. So if you check the specific volume, then you will see that it will correspond. If you take the inverse of this, it will correspond to about 1,000 kilogram per meter cube. Okay, so it does not necessarily change that much. And even if you look at the specific volumes here, you will see that it does not necessarily change that much. And if you take the inverse of all these numbers, remember this number times 10 raised to power minus 2. If you take the inverse of them, they will give you something like 999 or something like that, close to 1,000. So we can take a guess, calculated guess, that the density of water at that average pressure will give you 1,000 kilogram per meter cube. And if you take the inverse of that, it will give you the specific volume, which is 0.001 meter cube per kilogram. Now, if we multiply that against the difference of pressure and taking account the negative sign that comes with the formula, remember this formula from our ITF, and I think the first lecture we did as well, we explained all of this. Then you get the value for the work done by the pump. And if we add that value for the work done by the pump to the enthalpy at stage 1, and that will give us the enthalpy at stage 2. Okay. And remember to convert your pressures to pascals instead of working with bar. So that's to be consistent with the units. Okay. So at stage 3, what would be the enthalpy at stage 3? So because at stage 3, we know that we are operating at 30 bar and we are working with saturated liquid, then the enthalpy, we read out the corresponding enthalpy and entropy values for saturated liquid at 30 bar from the steam table. Okay. Now, once we've done that, we move over to find the enthalpies at the enthalpy and entropy at stage 4. So we do similar thing. We know that when the saturated liquid leaves the boiler, is totally converted to saturated vapor as to stage 4. So what happens? We go to pressure at 30 bar and we find the corresponding values for entropy and enthalpy. Entropy and enthalpy when the pressure is 30 bar, and that will be for the stage 4. Now at stage 5, we go to when pressure is constant at 30 bar, but the temperature increased to 450 degrees Celsius, which is superheated. Then we go to the superheated section of the steam table. So where is, you go to here, superheated section of steam table, we look for pressure at 30 bar. So if we scroll down, we have 30 bar. If I blow this up, so pressure at 30 bar, where is 450? So this is 450. Let me get it in the screen. So I hope you can see this. So we go 30 bar, go towards this, and we read the last two values here. Okay, the last two values here, 3343, and entropy, which is S, which is 7.082. Okay, 3343, 7.082, and that will be the enthalpy, the energy enthalpy physical properties at stage 5. Okay, so we go to stage 6, and we know that stage 6 is a mixture of saturated liquid and vapor due to the low quality steam leaving the, after performing the work in the turbine at stage 5, the low quality steam leaves the turbine to go into the stage 6 where the condenser is. And we know that there is existence of two phases, which is the liquid phase and the vapor phase. So we need to find the at pressure of 0.04 bar, the enthalpy and entropy for the two phases. Okay, so we can find those values at 4 bar, but we need to make sure that we know the quality of the steam, the exact quality of the steam. Now, with the help of this being asymptotic, meaning that stage 5 and stage 6 are the same entropy, okay? So the entropy at stage 5 is still the same entropy at stage 6, and with that information, we can calculate the quality of the mixture here, okay? So with this axis, S6, which is entropy at 6, is the same as entropy at 5. So because this is an asymptotic process here. So with that value, if we plug it in this equation, remember the dryness fraction, quality. We have done this in previous lectures. Please refer to those notes and lecture notes to see where we got this formula. And you can plug in the values for 0.4 with respect to the fluid, the liquid phase, and the gas phase, to get the quality, which is 82.7%. Now, since we know the quality as 82.7%, then we can finally calculate the combined enthalpy, considering the gas phase and the liquid phase. Okay, and we use the same dryness fraction or quality formula to do it, but in this case, calculating it for enthalpy. Okay, so here we plug in the value of x and x, and we already know this value from steam table. Then we multiply out and add, and we find the corresponding enthalpy at stage 6. And now we have all our enthalpies and our entropies. Then we can now calculate the first question, which says calculate the heat transferred in and out of the system. So we know that the inlet, the total heat added to the system is between 2 to 5. So what do we do? So we calculate Q in, which is between stages 2 to 5, which is the change in enthalpy between the 2 and 5, and that gives us H5 minus H2. So we know H5 and we know H2, and that will give us the total latent heat added to the system. Okay. Now the heat out of the system is between 6 and 1, so we need to find what happened. So we need to find the enthalpy, the change in enthalpy between 1 and 6, and that gives us minus 2012.1. Now the difference between these two will be the work done, okay, the work done by the steam. So, but the work transfers, so if we've already calculated the work done at the pump here, so what about the work done by the steam? We can do that by accounting using the enthalpy between these two. So the enthalpy between that two is that, okay? So it gives us this value. So we've calculated the work done by the pump and the work done by the steam at the turbine. So what about the cycle efficiency? We know the formula for efficiency as the net work divided by the total amount of heat added to the system. So the net work is given as the difference in the work in and the work out at the top here. So we know that the work out is this, and the subtracted from the work added to the system. Then that will give us the net work divided by the total heat added to the system between the stages 2 to 5. And that gives us a cycle efficiency of 37.4%. So calculating the specific steam consumption, remember again, I will say this is absolute value. That's what we want inside here. So meaning that even if there's a negative calculation here, the absolute cancels it out, okay? And we use this formula to calculate it. And the steam consumption rate is almost 3 kilogram per kilowatt hour, okay? For per kilowatt hour of energy produced, we consume up to near 3 kilograms of steam. Okay. So what about the work ratio? The work ratio is given as the net work divided by the work output of the steam. Okay. So the net work, as we know, is the work done by the steam subtracted by the work done by the pump divided by the work done by the steam, and that gives us a work ratio of 99.7%. So the superheated steam is used instead of saturated steam, and the average temperature at which the heat is supplied is increased, and this results in increase in cycle efficiency. If you check the first Rankine cycle without superheat, then you find out that there is a difference between the cycle efficiencies and the addition of this the addition of this superheater that converts the steam to superheated steam increases the efficiency of the cycle. So as the work ratio is so very near to unity in the unsuperheated Rankine cycle, the slight increase obtained by superheating makes very little difference. There is very little change in susceptibility to irreversibilities. So despite this, the specific steam consumption is markedly reduced and the net work per unit mass of steam is much greater. The added complexity introduced by the superheater is therefore compensated by a reduction in size of other parts. Okay.